This is such an important concept, and it's misunderstood by a lot of low-carb folks. There is no such thing as insulin resistance without hyperinsulinemia. That's very important because there are some instances called physiological insulin resistance, where the body has become insulin resistant to serve a valuable purpose. And overwhelmingly, that's growth. And that's why you only have physiological insulin resistance in two situations, pregnancy and puberty, because those are the two periods of rampant growth in a human, in the adolescent or in the adult female, of course. Regardless whether it's harmful insulin resistance, like I study in my lab, the kind that's connected to Alzheimer's, et cetera, or whether it's physiological insulin resistance, when the body's become insulin resistant for a period of time on purpose, it still is both of these aspects. Its insulin is altered in how it's working, and blood insulin levels are elevated. In other words, hyperinsulinemia. And a perfect example of this, Anthony, when we look at these two sides of the coin, it's to look at the two most common forms of infertility in males and females. Specifically, I mean erectile dysfunction and polycystic ovary syndrome, respectively. And in erectile dysfunction, it's a problem of the insulin resistance part of this coin, side of the coin, which is that insulin isn't able to promote sufficient vasodilation in the man anymore. And so not only does he have probably elevated blood pressure, but if you can't dilate blood vessels, you don't have normal erectile function. And thus it's the insulin resistance that's contributing to the male form of infertility, the most common. In stark contrast, in the female, it's not the problem of compromised insulin signaling. It's more a problem of the hyperinsulinemia, because at her ovaries, she has cells in her ovaries that are capable of rapidly converting testosterone into estrogens. And that's a little known fact. All estrogens were once testosterone, and the ovaries convert that over very, very well at a much higher rate than the testes do in men. However, insulin inhibits that conversion. And so as she's insulin resistant and her insulin levels are higher, that has a specific effect at the ovaries, where it's the elevated insulin, not the insulin resistance per se, that is preventing her ovaries from converting the testosterone into estrogens at a high enough amount. Now her testosterone's too high, her estrogens are too low, and then she has polycystic ovary syndrome. She isn't ovulating, she may have more coarse body hair, and so on. So people have heard of this concept of metabolic flexibility, which is a body that can shift between glucose and carbs really well, or glucose burning and fat burning, rather, really well. The average individual, because they have chronically elevated insulin, is essentially stuck in glucose burning. Even when they start to fast, which should shift their body to fat burning, they don't. They stay in glucose burning. Well, if you're a carnivore, it's almost like you're stuck in fat burning. And the body has a little bit of a reluctance. You've lost a little bit of that flexibility. Now, I wouldn't say that's a bad thing. I think it's fine. If you're going to be anywhere, be in fat burning mode. But it does make it a problem if you come dump the body with full of glucose. Well, it takes a little time to shift back. It's a little resistant. It's a little inflexible. Now, thankfully, you can go back to perfect flexibility after like a day, eat some carbs one day, the next day, you're right back to where, if you want to be there, well, that's where you are. Now, again, I'm not saying that that's something healthy or needs to be done. You know, that's, some people might hear what I'm saying and then think, well, that's why I need to cycle in and out of carnivore or ketosis. No, I'm not saying that.
You don't lose that at any point. So if you were carnivore or keto for a number of years, would you be able to snap back into it if you needed to?
Within a day.
Yeah.
Absolutely.
Perfect. Yeah.
All it takes is one challenge to the beta cells. And then they say, okay, we're doing this again. No problem. I can do that.
Yeah. And probably, since they've been rested for so long, they're not going to be, they might be even more ready to go. And whereas, sometimes you can get, a type 2 diabetic, you can burn out your beta islet cells and now become insulin dependent. Which happens to quite a lot of people more and more. It sounds like the insulin relationship and response sort of sounds like a bit of like tolerance to like drug or alcohol tolerance, where you have this buildup in different sorts of enzymes to you're anticipating, your body's anticipating this this toxic exposure, and you're trying to sort of mitigate that and be ready for it. It sort of sounds like your body's doing that with insulin as well. It understands there's just going to be an abnormal amount of carbohydrates coming in, which can cause harm, hyperglycemia, causing glycation.
When insulin is working, it has a vasodilatory effect. It's one of insulin's lesser known actions, but it's just further proof that insulin literally affects every part of the body. Every single cell of the body has insulin receptors, which really makes it really unique among hormones, because not all hormones, in fact, few hormones do that. But one of insulin's effects is when it binds the cells of the blood vessel, it will induce the production of a molecule called nitric oxide. And nitric oxide, I'm sure your audience knows, it's a potent vasodilator. That's basically what, if someone's experiencing chest pain, they go in and they give them nitroglycerin. It's because the nitroglycerin will help stimulate this nitric oxide throughout the body, and it will throw open the blood vessels, for example, of the heart, and then the chest pain goes away. But to another degree, that's what's happening around the body. But in the case of the insulin resistant man, when his blood vessels have become insulin resistant, well, that's not working as well. And so insulin's trying to promote vasodilation. It can't, and the blood vessels stay constricted. Now, systemically throughout the body, as the vessels are more constricted, the narrower that volume is, of course, the higher the pressure goes. Those are inversely related. As volume's dropping in the chamber of the blood vessel, it's pressing in on the blood more, which increases pressure. And one group found that ketones actually will bind to cells and inhibit something called the NLRP3 inflammasome. Ome as a suffix just generally refers to like a sum, like the entirety of whatever it is you're looking at. And so the inflammasome essentially evokes this idea of something that is in charge of all inflammation. And that's not too far from the truth, where this molecule NLRP3 essentially, if it's activated, it will essentially turn on all of the machinery to produce all of these pro-inflammatory cytokines and initiate immune systems throughout the body. Now, of course, we need a healthy immune system, so this can't be viewed as a bad thing, but you want it to be turned on when it's supposed to be turned on and turned off when it should be turned off. One of the problems with obesity, or even not overt obesity, but just fat cells that are getting too big, even if the person's just modestly overweight, is that they become pro-inflammatory. And this is why weight gain is associated with it's sometimes called a subclinical inflammatory state, where it's subclinical because it's not like the person's coming in with some raging fever, but in fact, the inflammatory markers are higher than you would expect in an otherwise healthy person. So in these instances where you have kind of aberrant activation of the immune system and inflammation, it's valuable to know, how can we turn that down? How can we turn down this aberrant inflammation? And ketones will do that. When ketones, and this isn't because of their energetic or their caloric value, it's because they can bind to these things called G protein coupled receptors. But there are so many different types that ketones will bind a particular type, and in so doing, act like a hormone, binding this surface receptor, just like a hormone does, initiating a series of events that result in the inhibition of this key inflammatory signal. We've specifically looked at the signaling capability in fat cells, and we found that when ketones come to fat cells, including fat cells in humans, that it starts to activate an uncoupling process at the mitochondria. Now, briefly, all that means is basically the ketones result in the mitochondria in fat cells being much more active. It basically stimulates the metabolic rate in the fat cells by about 2 or 3 times over normal. And again, that's not because the ketones being burned for energy. It's because there, once again, is a G protein coupled receptor on the fat cell that is activated when ketones come knocking, and then that tells the cell to do something. That yes, ketones are an energy. That's why, the brain so greedily pulls in ketones, because it has an energetic value. It has a caloric value roughly similar to glucose, about 4 calories per gram. But independent of that is its signaling capabilities, which is just like the cherry on top of the low carb cake, where it's really, these are molecules that again are an energy source, maybe desperate for the brain, or the brain becomes desperate for it. So it's a very good, viable energy source, but also a good and viable signaling molecule that provides an anti-inflammatory and even, dare I say, metabolic benefit. When I first kind of became aware of the low carb community, when my lab had started studying the effects of ketones on fat cells, and in that very first early work from my lab, one of the organizers of a low carb event, it was called at the time Low Carb Breckenridge, And these guys reached out and said, hey, we're aware of what you're doing. We'd love for you to come give a talk at our meeting. That was my first exposure to the community and the kind of keto community at large, coming in as a scientist. And I was so interested by what I saw and heard, which was a fear of protein, to your point, where people were saying, oh, well, I saw, they were drinking oil and, adding butter. And I thought, this is so bizarre. And then and a lot of it was born from this fear of protein, which itself came from the original ketogenic diets that were used to treat epilepsy.
Right.
And it was such a necessity to keep the person into deep ketosis that you didn't want to mess with that at all. You didn't want to do anything to potentially blunt those ketone production, the ketogenesis, lest they have an epileptic seizure. So tremendous reason to want to be in strict deep ketosis all the time. Well, the fact is insulin can increase in response to dietary protein. That can happen. And if insulin goes up, well, then ketogenesis or ketone production will drop. But I nevertheless thought it was tremendously a misplaced fear. And then the next time I spoke at this same meeting, that was the topic I spoke on. It was basically helping people understand the fact that they need not be afraid of any modest increase in insulin that comes from dietary protein, because if it happens in the context of a low carb diet, then the commensurate increase in insulin's opposite is glucagon, namely, is greater than or equal to what the change in insulin is. And that matters. So in other words, if you eat some protein and you're eating it with carbohydrate, which in nature never happens, never. In nature, protein comes with fat. It doesn't come with carbs. Nevertheless, if you eat your protein with glucose, then you get a big increase in insulin, bigger than it would have been if it was just glucose alone. So no question, the protein adds to the insulinogenic effect of a carbohydrate. But also, they're not supposed to come together. If you eat the protein with the fat and there's no carb, well, then there may be a modest insulin increase, but there's a relatively greater glucagon increase. And glucagon is insulin's opposite in many, many ways, including ketogenesis. So whereas that little elevation in insulin is trying to inhibit the production of ketones, that relatively greater increase in glucagon is overcoming that and, in fact, acting more as a stimulatory effect. So offsetting the modest increase in insulin. So to wrap all of that up, my concluding thought is for the average individual who's focusing on just improving their health, no reason to fear protein, but be smart about it. Don't eat your protein with carbs because you will, in fact, amplify that insulin effect.
The brain, when I was taking biochemistry, 20, 22 years ago, we were taught it was ketones. Your brain optimally runs on ketones. It preferentially runs on ketones, especially when you're in a so-called fasting state, which I argue is not a fasting state. I argue that that's our primary metabolic state. Mm-hmm. That's the metabolic state of most animals in the wild. If you look at them,
that's our natural state. Our natural state isn't putting something in our mouth. I am putting together a session, and it's all about the changes in human diets over, our ancestor diets over these periods of evolution. And I want you to talk about the brain acting as a hybrid. And in my preparation for this talk, I found a paper that had been published in like the most dynamite anthropology journals, the Journal of Human Evolution, I think it was called. I don't really remember, but it's their really great journal that everyone wants to publish in. And in that article, I found it was all about how the Neanderthal diet and the development of the brain. And they had two comments in there, both of which reflected a profound ignorance by stating that dietary carbohydrates are essential and were essential to our ancestors in the development of their brain. And I actually cited that article, and then I just kind of hopefully tactfully just said, this is wrong. And then shared with them a quote by the National Academy of Sciences in the US stating that the lower limit of carbohydrates in the human diet is 0. Yeah. In other words, there is no such thing as an essential carbohydrate. And the idea that the human brain evolved because our ancestors ate a lot of carbs, that's utterly ridiculous. And that's basically the impression I gave the audience, hopefully not too offensively, but I had many, many people come up to me afterwards, very, very grateful maybe the haters and the detractors didn't bother coming up, but no one uttered a negative word. It was just absolute gratitude at learning this reality of human biology and physiology, which is that, yes, it's because they mistake dietary carbohydrates with blood glucose. That it appears, what does appear to be the case is that the brain has some demand for some glucose. That appears to be accurate, although the lower limit is unknown. Early work by a fasting physiologist named George Cahill, he was putting people's glucose down to like 20 milligrams per deciliter, which most people would say you're unconscious, you're in a coma and you're going to die. And these people, because they'd been long-term fast adapted, which I would say ketone adapted, there appeared to be no deficit to cognition. I mean, that's a pretty bloody low level of glucose. But nevertheless, let's kind of grant that side of it, that the brain has some requirement for some glucose. Well, it is a minimal requirement, because if you take a body that has 5 millimolar glucose and you start increasing the ketones to 1 or 2 or even 3 millimolar, which is still less than the 5 millimolar of glucose, so there's still less of the ketone in the blood than there is the glucose, by then the brain has already dramatically shifted its energy use. And even though the ketone may be less than half of what the glucose is in the blood, it's now providing double, twice as much of energy to the brain as the glucose is. So if the brain has any preferential fuel, it is absolutely for the ketone. You can take a newborn baby and the baby can breastfeed or bottle feed. And then within an hour, the baby is in a deeper state of ketosis than an adult would be after fasting for a full day. And I mean, so if there's any natural state, kind of back to our conversation a moment ago, it is clearly that a natural state is a state of ketosis.
It was all about honey, and how they're arguing that honey was probably the causative factor of our brains growing so big, because it's the most nutrient dense, is the most calorically dense substance. And my initial response was like, do you know what the word density means?
I know.
Yeah, it's calories.
That's what I'm talking about. That's what I'm talking about. Yeah. It's like, just stay in your lane.
Yeah, exactly.
You anthropologists, and in all seriousness, they were incredible scientists, and I was thrilled to meet them. But clearly, there's just this bit of a disconnect. I shouldn't say stay in your lane. That's part of the fun of academia. It's going out of your lane for a moment. But to make that kind of statement about honey, look, I'm not trying to declare war on honey. I know that in the carnivore community, there are some very outspoken advocates. I think it's clear that our ancestors, our hunter-gatherers, it's clear that if people can get honey, they're going to love it. And they want to eat honey. But to then say that that was the fundamental food in brain development, well, the brain isn't made of honey. The brain is made of proteins and fats, especially a lot of fat. I mean, and you need these essential fats from meat in order to have sufficient brain growth. You don't get any of those from honey.
People obviously, like the Inuits living in by the North Pole, or our ancestors coming through the ice ages, there was no honey and there was no fruit. And so, I'm certainly in the other side of the camp where I'm saying, honey's actually really bad. It's bad for you. Fruit can be bad for you. Fructose, Dr. Lustig from UCSF has done yeoman's work showing just how harmful fructose is. But then some people say, well, in the context of honey and this, and fruit, maybe it works differently. And that may be true, but they haven't actually provided any evidence that it does. Getting a runner's high, getting your second wind. A lot of endurance athletes and a lot of just athletes in general have certainly heard about this, and some have experienced it, where you push yourself, you're exercising very, very hard, or you're running a great distance, and you eventually run out of energy. You hit the wall and you feel awful. You're just like, that's it. You're cashed out. Most people stop at this point, but then there are people that have pushed themselves and pushed themselves and pushed themselves, and then eventually they break through the wall. They get their second wind, and then they can just go forever, and they feel amazing. What I think is happening there biochemically is that they're in this hyperglycemic, insulin-driven state, and so insulin is stopping your body from mobilizing your energy from your fat, and so you're going to have blood sugar, you're going to have liver glycogen and muscle glycogen that you're going to be running on, and especially if you carbo load, and that's why they do that. But eventually you're going to run out. This is a finite resource. Whereas in studies we've seen in wolves in 1981, because they said, you need to eat carbs or burn carbs. They said, well, wolves don't carbo load before they chase caribou for 10 hours. Do they even have blood sugar? Do they even have glycogen? They found out, yes, they do. And it's rock solid. It doesn't change. Their body's constantly replenishing it. And so when you're eating carbohydrates, exogenous carbohydrates, that's going to curtail that, and that's going to stop that process. And now you're going to run out of energy. And normally it takes something like 16 to 24 hours before your insulin comes down low enough that you can actually start producing more of your own energy. And that's usually it for everyone. But if you push yourself, I would imagine what's happening here is that you're actually forcing yourself to get back into a state where you can mobilize ketones, make your blood sugar, make more liver glycogen, and then you just get into this runner's high, and this second win,
steady state.